Welcome to the lecture on Advanced Calculus and Numerical Methods. In my previous lecture, I discussed about the ordinary differential equations and solving of homogeneous and non-homogeneous differential equations by using various techniques. So in this module 3, I am going to discuss briefly about the partial differential equation and the formation of partial differential equations by using eliminating arbitrary constants and also by using eliminating arbitrary functions, and also how to solve the homogeneous and non-homogeneous partial differential equations by using various techniques. And also I am going to discuss about the applications of partial differential equations like heat equation, wave equation, and the solution of heat and wave equations by using variable separable methods. So first let me define what is meant by partial differential equations. An equation involving one or more partial derivatives of a function of two or more independent variable. So in the sense, the same function, the same dependent variable will be having two or more independent variables here. So A is known as partial differential equations, or we can call it as an PDE also. The highest derivative gives the order of partial differential equation, and the positive integral power of highest derivative gives the degree of the partial differential equation. So this order and degree will be same as of the ordinary differential equations. So now a note on the partial differential equation. So let z be a function of two independent variables x and y. So as I told that in the partial differential equation, one dependent variable will be having two independent variables here. So like that, so let z be a function of two independent variables x comma y, and the following are the standard notations here. First one is, we can replace dou z by dou x. In the sense, differentiating z with respect to x can be written as p, small p, or we can write like zx. Similarly, dou z by dou y will be equal to q or zy, and dou square z by dou x square. So differentiating dou z by dou x with respect to x again. So it can be written like r or z double x. Similarly, yes, s is given by dou square z by dou x into dou y. In the sense, differentiating dou z by dou y equation with respect to x. So I will get dou square z by dou x dou y, or dou square z by dou y dou x. Differentiating dou z by dou x with respect to y, I will get dou square z by dou y dou x. So it will be equal to z xy or zyx. So in the problems, we can use these notation to simplify the partial differential equations also. One more is t. T is nothing but dou square z by dou y square. It can be denoted like z double y. So now in the partial differential equation, the first concept is formulation of PDE by eliminating arbitrary constants. So here one equation will be given. That equation will have the independent variables and the dependent variables and also few arbitrary constants. So we have to frame the partial differential equations by eliminating the arbitrary constants here. That is, consider the function f of x, y, comma z, comma a, comma b will be equal to 0. So where z is a function of x and y, so where z be a dependent variable, x and y be a independent variable for z. With a and b are arbitrary constants, the PDE of the function f is formed by differentiating f with respect to x and y and eliminating arbitrary constant. So after differentiating, we have to eliminate the arbitrary constant and we have to frame the partial differential equations here. And if the number of arbitrary constants exceeds the independent variable, say for example, in this we can see here we having two independent variables with two arbitrary constants. Suppose if two independent variables, if three arbitrary constants is there, means we have to follow this procedure here. That is, if number of arbitrary constants exceeds the independent variable, then it is very important to find the higher derivatives to eliminate arbitrary constants and form the PDE. So higher derivative in the sense we have to find dou square z by dou x square, dou square z by dou y square, dou square x, dou z by dou y, we have to find it. Then we have to eliminate the arbitrary constants in these cases. So examples: form the partial differential equation by eliminating arbitrary constants in the following function. The first function is z is equal to x minus a whole square plus y minus b whole square. So here we can see that z is a dependent variable, x and y are independent variables, and a and b are arbitrary constants here. So now, as I told that we have to differentiate the equations first to eliminate the arbitrary constants. So given equation is z is equal to x minus a whole square plus y minus b whole square. Call it as equation number 1. So on differentiating equation number 1 with respect to x, I will get dou z by dou x, and from PDE we have dou z by dou x will be equal to p. So on differentiating this with respect to x, I will get 2 into x minus a, so y will become 0. Similarly, differentiating equation number 1 with respect to y, I will get dou z by dou y, so it will be equal to q, and differentiating this equation with respect to y, I will get x will become 0. Y minus b whole square will be 2 times of y minus b. Call it as equation number 3. So now we can see that I can write x minus a is equal to p by 2, y minus b is equal to q by 2. I can replace x minus a and y minus b in the equation number 1 to eliminate the arbitrary constant. So if I replace those values here, the constants get eliminated, only PDE I will get it here. So like that I'm going to do now. So using 2 and 3 in the equation number 1, I got the equation like z is equal to p by 2 whole square plus q by 2 whole square. It will be equal to z is equal to p square by 4 plus q square by 4. Shifting this 4 to LHS, I got the equation like 4z plus p square plus q square. So this is the required partial differential equations with no constants here. Okay. So next problem. 2z is equal to x square by a square plus y square by b square. So here z is a dependent variable, x square and y square are the independent variable, a square b square are the arbitrary constants here. So we have to eliminate this a square b square from the equation. So first take the given equation as equation number 1. So differentiate equation number 1 with respect to x. So I'll get 2 times of 2 I'm keeping as it is only. Differentiating z with respect to x, I will get p, that is dou z by dou x. So differentiating x square, I will get 2x by a square, y will become 0. So I will get I can write 1 by a square here. So constant 2 I cancel here. So I will get 1 by a square is equal to p by x, I can write it, or I can write p is equal to x by a square also. Call it as equation number 2. So next is differentiating equation number 1 with respect to y. So z will become dou z by dou y, it is nothing but q, so I'm getting 2q here. 2q is equal to 2y by b square, x will become 0. 2 gets cancelled, I got q is equal to y by b square. Call it as equation number 3. So now replace x by a square is equal to p in this equation, y by p square is equal to q in this equation to get the partial differential equation without arbitrary constant. So we'll get 2z is equal to px plus qy. Since here x square y square is there, I am rewriting x square as x into x by a square, y square by b square as y into y by b square. So I can use these two values. So I got the equation like 2z is equal to px plus qy is the required partial differential equation. One more, z is equal to a into log of x square plus y square plus b. So from this we have to eliminate the arbitrary constants, we have to frame the PDE. So first take the given equation as z is equal to a into log of x square plus y square plus b, call it as equation number 1. So differentiating this with respect to x, I will get p is equal to 2ax by x square plus y square. Since here no term, so constant will become 0. I'm keeping a as it is. Differentiating log I will get 1 by x square plus y square. Differentiating x, I will get 2x there. So I got 2x by x square plus y square. So similarly differentiating equation number 1 with respect to y, I will get q is equal to log will become 1 by x square plus y square, keeping a as it is, and differentiating y square I will get 2y. So I got the equation like 2ay by x square plus y square. So here we can observe that we could not able to find the value in terms of b here. So what I will do means I'm going to divide these two equations to eliminate the constant a. I'm going to make the partial differential equation because here I could not able to find the value of b. So only replacing the value of a means the b cannot be eliminated. So I'm going to divide the equation p and q here. So I can able to frame the partial differential equation. So dividing p by q, I got x by y. So on taking LCM, I'll get the equation like py minus qx is equal to 0 is the required partial differential equation. One more, z is equal to xy plus y into square root of x square minus a square plus b. So same thing here, take the equation as z is equal to xy plus y into square root of x square minus a square plus b. Call it as equation number 1. So differentiating equation number 1 with respect to x, I will get p is equal to, so x will become 1. So only y I will get it here, y plus xy into square root of x square minus a square. So on differentiating this square root, I will get 1 by 2 into square root of x square minus a square. Differentiating x square, I will get 2x here. 2 gets cancelled. So I got the equation like y plus xy by square root of x square minus a square. So similarly, differentiating the same equation with respect to y, I'll get p is equal to x into, so only y will become 1. So it contains only x term. So I can keep the square root of x square minus a square as it is. B will become 0. Call it as equation number and I can rewrite this x square minus a square as q minus x. So since here I could not able to estimate the value of the equation in terms of b, so I can't eliminate b directly here. So for that, I'm making square root of x square minus a square value as q minus x. I'm going to replace this value here to eliminate the constant a square here. So if I replace this value in this equation, so I will get the equation like p is equal to y plus xy by q minus x. On taking LCM, I will get on shifting y to LHS, I got p minus y, and into q minus x is equal to xy. Or on expanding this equation, we got pq minus px minus xy plus xy is equal to xy. Xy gets cancelled. We got the equation like pq is equal to px plus qy is the required partial differential equation. One more example. Function is z is equal to ax plus by plus cxy. So here we are having three arbitrary constants, but we are having two independent variables. So we'll see how to differentiate and how to eliminate the constants here. So given z is equal to ax plus by plus cxy. So call it as equation number 1. So differentiating 1 with respect to x, I'll get p is equal to a plus cy. Call it as equation number 2. If I differentiate equation number 1 with respect to y, I'll get q is equal to b plus cx. Call it as equation number 3. So here I could not able to eliminate the constant c. Only a and b I can try to eliminate, but c I could not able to eliminate also. So what I will do means I'm going to differentiate equation number 2 with respect to x. I'll get dou square z by dou x square is equal to, since both are constant, no x term here, the complete term will become 0 here. So I can replace this as r is equal to 0. I got it. Similarly, I'm going to differentiate q with respect to y. So in q also no y terms at all. So if I differentiate that equation, I will get t is equal to 0. So now differentiate 1 with respect to y. So on differentiating the equation number 1 here, with respect to y, I will get dou square z by dou x into dou y into dou x will be equal to, a will become 0, only c term I will get it. So since y will become 1, only c I will get it. So I got the value like s is equal to c, I can write it. So on replacing that dou square z by dou y dou x as s, it will be equal to c. So now using equation number 2, 3 and 6 in the equation number 1. So since I want to eliminate the values of a, b, c, I'm going to use equation number 2, 3, 6 in the equation number 1. I get the equation like z is equal to p minus sy into x. So before that, I'm going to replace c is equal to s in these two equations. I'm going to make the equations in terms of a and b from these two equations. I'm going to replace those a and b values along with a c value in the equation number 1. So I will get the equation like this here. Z is equal to p minus sy into x, q minus sy sx into y plus sxy. On simplifying this equation, we got the equation like z is equal to px minus sxy plus qy minus sxy plus sxy. So this way I can cancel it. So I got the equation like z is equal to px plus qy minus sxy is the required partial differential equation. So one more problem is x square by a square plus y square by b square plus z square by c square will be equal to 1. So same thing also we are having two independent variables with three arbitrary constants. So differentiating the equation number 1 with respect to x, I got the equation like 2x by a square plus 2z into p by c square is equal to 0. So I can write x by a square plus zp by c square is equal to 0. Call it as equation number 2. So differentiating 1 with respect to y, I will get 2y by b square plus 2zq by c square is equal to 0. It will be equal to y by b square plus zq by c square is equal to 0. Call it as equation number 3. Since I could not eliminate the constant c also here, I am going to differentiate equation number 2 with respect to x again. So I got the equation like 1 by a square plus 1 by c square into zr plus p square. It will be equal to 0, or 1 by a square is equal to minus times of zr plus p square by c square is equal to, I will get it. So I will call this one as equation number 4. So on replacing this equation number 4 in equation number 2, I got the equation like minus of x into zr plus p square by c square plus zp by c square is equal to 0. I can take LCM, I can shift this c square to RHS, so it can eliminate. So on simplifying this equation, I got the solution of the partial differential equation like zp is equal to zrx plus xp square is the required partial differential equation. So in the next lecture, I am going to discuss about how to eliminate the arbitrary functions. Thank you.